Hey class, and welcome back. We're going to now do an introduction to chapter 11, which is really just a continuation of chapter 10. So you'll see chapters 10, 11, and 12 are all really kind of grouped together. As I mentioned before, they're almost a repeat of everything we've done in the class up till now, applying it to things that are rotating, applying it to rigid bodies that have the freedom to both translate and rotate at the same time. So yeah, we're going to continue on with chapter 11, which is very similar to some of the things we saw in chapter 10, looking at additional applications of moving objects that are rotating, and then introducing angular momentum and talking a little bit about torque in 3 dimensions before we move into chapter 12, which we're going to be applying torque to equilibrium systems, and then also talking about in chapter 12 elasticity and the fact that things, when they're experiencing forces, have a tendency to actually change size or shape just a little bit due to the elasticity of materials. But that's chapter 12. Anyway, chapter 11, rotational motion, again with angular momentum as well. So first of all, just to kind of summarize where we left off last class, we can have objects that are moving, right? They're translating, as you see here. So you can think of this as being like an object just moving in a straight line, or here I have my trusty tennis ball, so it can be moving in a straight line. Or you can have an object that's rotating. So again, I can have my tennis ball rotating like so. And then you can also have an object that rotates while also translating. And that's what we see here. So for an object that's rotating while translating relative to the ground, at this point where it's in contact, its velocity at that instant is actually 0, right? If it's rolling on the ground, you can think of it for just a brief moment, that point is stationary as the ball continues to move on because it's pushing with static friction, right? So if it's static friction, it must be static, not moving. Whereas up here at the very top, because it's translating and rotating, it's actually moving twice as fast, this upper edge, as the center of mass of your object. And at different points, it has different velocities, as you can see here, a combination of both of these. But keep in mind, remember, we can relate, if this is rolling without slipping, we can relate the velocity of the center of mass of our wheel or object to the angular velocity of our object, because v center mass is just equal to r times omega. So when things are rolling, as I just implied, right, it's friction that causes them to rotate, right? Without any friction, my tennis ball would just translate down a slope. But as friction catches on that bottom edge of the ball, it makes it rotate as it goes down. So friction pushing backwards on the bottom surface forces the wheel to start to rotate. Okay, so this is for like a ball going down, or like a wagon. If you pull a wagon, the wheels rotate as a result of friction pushing backwards. This is different than wheels that are powered. So like in my Subaru, it's 4-wheel drive. All wheels are powered by the engine. As they are powered, as they're trying to rotate from the engine, friction actually pushes those forward, whereas here friction is pushing backwards. So this is really kind of a confusing topic for people sometimes. But for a wagon wheel, again, if you have your wagon and here are your wheels, right? This is big tires on my wagon here. As you pull the wagon this direction, without any friction, everything would just move forward, right? It would just slide forward and there'd be no rotation whatsoever. But as it's trying to slide forward at this point of contact, there's friction opposing that motion, friction pushing backwards on those tires, and it's that backwards pointing friction that causes it to rotate. Maybe it's a little hard to see, so I'll make it a little bigger. So again, as it's trying to slide forward from the pull, there's friction pointing backwards at the bottom of these wheels, which causes them to then rotate. Whereas a powered wheel, such as the wheels on my Subaru, which are in 4-wheel drive, or which has 4-wheel drive. Okay, I'm not an artist, so just bear with me. This is my beautiful vehicle here. Okay, so here's my Subaru. Here's me driving. In this case, the engine makes the wheels rotate. So the wheels are already rotating. If there's no friction, you would just be peeling out. You wouldn't go anywhere. If there's no friction here, you'd just be able to pull it forward, and it would just slide on the ground. So in this case, the wheel is rotating, so at the ground, the wheel's moving backwards, so friction force is going to be pointing forward. So in this case, your static force of friction is forward, propelling you. Here, your static force of friction is backwards, causing the wheels to turn. So just wanted to clarify that, make sure you guys understood the difference between those. So here I have a ball rolling down a hill, and the friction is pointing up the hill, causing it to rotate rather than just slide. Now we're going to usually assume things are perfectly rigid, so we're going to use this model that you see here. But keep in mind, this is really an approximation. Just like we have friction in the natural world, we also have rolling resistance. And what rolling resistance is a result of deformation of your surfaces. And so that means you end up with the force being occurring slightly ahead of the center or of the point of contact that you would normally approximate. Your friction force and your normal force are both basically moved slightly forward just a little bit on the ball, as you see here, and that results in actually a torque that slows down the ball just a little bit. I think the mailman or somebody's here. I don't know if you guys can hear my dog barking in the background, but he's letting me know that a package is being delivered. Anyway, so again, we're going to assume perfectly rigid, so there's no torque causing it to slow down, but in reality, due to small amounts of deformation in the surface, you do have a resistive torque. All right, so let's do a quick example problem. All right, so let's imagine a bowling ball that's going to be rolling down without slipping on a ramp. So, you know, when you, after you bowl, then it comes out of the machine and there's sort of this little ramp that it rolls down as it pops out to you. So let's model that, all right? So we know it's friction force that's causing it to rotate. So I want you to tell me two things. One, what is the acceleration of the ball down the ramp, assuming it's at an angle beta? And the second thing is I want you to tell me what is the force of friction. And I want you to model the ball as a solid sphere. Pause the video and try it out. All right, so hopefully you paused the video and tried it out. Hopefully you followed the process, starting with a picture. So here's my picture. It's accelerating down the ramp. And then here's my free body diagram. So I have a normal force perpendicular to the ramp. I have the weight force going down, and I have the friction force causing it to rotate, pointing up the ramp, right? So if you notice, I went ahead and broke my weight force into X and Y components, mg sine beta for the X, mg cosine beta for the Y, all right? And now I'm trying to find, again, the acceleration and the friction force. So to try to solve, what am I going to do? Well, I'm thinking forces, I'm thinking acceleration, boom, Newton's second law pops into my mind. So setting up some of my forces, I have mg sine beta in the positive X direction, since I'm calling down the ramp positive. I have force of static friction in the negative X direction, so minus force of static friction, and that equals ma. But as I look at this, wait a second, I don't know friction, and I don't know the acceleration. I got two unknowns in my one equation here, can't solve, so I got to go somewhere else. What else can I use? Well, some of the forces in the y, I got normal equals mg sine beta. That's cool, but it doesn't really help because I don't know even the coefficient of friction. But I have a rotating object, right? And kind of as this picture kind of might hint to you, there's a relationship between the acceleration of the center of mass and the angular acceleration of my object. Angular acceleration, forces at a distance, I think, oh, Newton's second law as it applies to rotational motion. So for this, if I'm calling the z-axis, the axis coming out of the picture shown here, right, I'm calling that the positive z-axis, then some of the torques about that axis will equal I alpha, Newton's second law. So what torques do I have? Okay, well, any force at a perpendicular distance can generate a torque. Normal force? Nope, it's acting at the center of mass, no torque. Weight? Also at the center of mass, no torque. The only thing left is my static force of friction acting at a distance r away from the center of mass. So my torque, it should be equal to r times the force of static friction. And then looking also at my equation, what is I? Well, I have a solid sphere. So for a solid sphere, I is 2/5 mr squared. Okay, good. So force of sum of my torques is the force of static friction times r equals I times alpha. Cool, we're getting closer. Now I got two equations, but three unknowns. Friction, acceleration, and angular acceleration. So I need to make the substitution that angular acceleration times r equals my acceleration of my center of mass down the ramp. So if I plug that in, canceling out one of my r's with the r on this side, I can now cancel out one additional r. And look at this, my force of friction is just 2/5 m times the acceleration of the center of mass. Cool. Now we can plug this into our other equation up here, mg sine beta minus force of friction equals ma. Get our a's together, so adding 2/5 ma to both sides, I get 7/5 ma. Oh, ma, no, 7/5 a because my m's cancel out, sorry, skipped that step. So all my m's cancel out, and 7/5 a equals g sine beta, so a is 5/7 g sine beta. Boom, box worthy. Again, we're asked to solve in terms of beta and m. We don't even need m for the acceleration. So we have that. And lastly, we're asked to find the force of friction. So I can plug this acceleration back in to my force of friction equation I already found here. And I discover that the force of friction is equal to, doing the math, 2/7 mg sine beta. Box worthy. So that one's a little bit of a tricky problem, but it's a good example problem as well. So hopefully that makes sense. Notice you need to get in the habit of doing this and practicing this, where you're doing some of the forces and some of the torques together. You're going to be having to do that time and time again with these rotating rigid bodies. You might have to also have some of the forces in the Y as well. And you'll see I'll do a few more complicated examples in separate videos for you as well. All right, so the next thing I want to define for you all is angular momentum. So if you remember, we already learned about linear momentum. Linear momentum, maybe if we don't recall, I'll put it up here on the board. But what we have is linear momentum is equal to mass times velocity, right? And now you're going to see angular momentum. We're going to use the letter L to represent angular momentum, is going to be equal to rotational version of mass, which is rotational inertia I, multiplied by angular velocity omega. So you see, time and time again, our equations for linear motion and rotational motion look very similar to one another, just swapping out the variables. If you don't remember, kinetic energy, 1/2 mv squared. Kinetic energy for rotation is 1/2 I omega squared. So time and time again, you see these equations that look very similar, just like we compared in the last video all of our rotational kinematic equations to our linear kinematic equations as well. So angular momentum is equal to I times omega. Keeping in mind, as always, we must make sure that we're using radians per second for our angular velocity, and then the units for I, moment of inertia, don't forget kilograms times meters squared. So angular momentum, keep in mind, is a vector quantity. Sometimes this confuses people. What direction is the vector quantity, okay? So remember, clockwise is negative, counterclockwise is positive, and you could use the right-hand rule to help you determine. What direction is the angular momentum of a wheel if it's kind of in the horizontal plane parallel to the ground? Well, if it's going counterclockwise, I do right-hand rule, the direction would be straight up. If it's going counterclockwise, right-hand rule, it would be straight down, okay? Now, what if I had a wheel spinning like this? Or let's do it this way so you guys can see it, okay? Spinning like this in a circular manner, just like this, right? By right-hand rule, if I put my fingers in the direction of the motion, my thumb is pointing at you guys. That would be the direction of the angular momentum, the same as the direction of the angular velocity. Now, if it's doing the same thing but going in the opposite direction, I would do the right-hand rule and it would be pointing straight at me, okay? So keep in mind the right-hand rule can help us determine the direction of the angular velocity. And if we look back here, right, the direction of the angular velocity is the exact same as the direction of the angular momentum, since I is a scalar quantity. So just a little reminder about the good old-fashioned right-hand rule. Okay, so angular momentum again is I omega, and you can use the right-hand rule to figure out its direction. Just like we saw before, net force is equal to the derivative of momentum. You remember that? Net force is the derivative of momentum with respect to time. Well, guess what? Same thing. Net torque is equal to the derivative of angular momentum with respect to time. So this can also help you think about the direction. The direction of your net torque is going to be the direction of your change in angular momentum. So that's where the derivative comes in. So again, keep that in mind as we move forward. And don't forget, right, net torque is I times alpha. All right, so now speaking of torque, I just want to briefly introduce how torque works in 3 dimensions. Many of you have not taken Calculus 3 yet, so you probably haven't done much with what's known as a cross product. But cross products are a really cool and powerful tool. It's a way of multiplying vectors together. So as I mentioned way back in chapter 2, there's really kind of 2 ways we can multiply vectors together. One is what's known as the dot product or the scalar product, because it gives you a scalar value. The second way of multiplying vectors is what's known as the the cross product, which is also sometimes referred to as the vector product. Okay, so what the cross product is doing, you can see here, torque is R cross F. All right, what the vector product or the cross product is doing is it's really trying to figure out how much 2 vectors are perpendicular to one another. Okay, so if you remember, the dot product tells us how much they're in the same direction. The cross product, it gives us an idea of their perpendicular relationship to one another. But as a result, you also get from the cross product a vector quantity. So to go into more detail with cross products, you're going to need more math. You're going to have to take Calc 3 and so on. But really, it's trying to tell us torque is force times perpendicular distance, right? So the cross product is looking at how much those 2 are in perpendicular relationship to one another. So if they're parallel, if they're perfectly in the same direction, the cross product would be 0, okay? So the magnitude of the cross product, again, cross product is a vector, torque is a vector. The magnitude of it can simply be determined by taking the magnitude of one of your vectors, f, multiplied by the magnitude of the other vector, r, and multiplying it by the sine of the angle between the 2. Okay, so if you have 2 vectors and you know their magnitudes and the angle, you can figure out the amount of torque generated by finding f times r times the sine of the angle. Which again, you probably have already determined from when we first introduced torque before. You could come up with a very similar equation as well. Okay, and then keep in mind the right-hand rule, as we were just talking about, can be determined using, the direction can be determined using that right-hand rule. Okay, so again, just to reiterate, there's a couple different ways you can do the right-hand rule, a couple different tricks people use. One is if you take your right hand and you point your fingers in the direction of R, your first vector, okay, point them in the direction of R, and then you imagine the direction of F, right? And so you set things up so that the palm of your hand is pointing in the direction of the vector F. So again, you put your fingers in the direction of R, palm in the direction of F, your thumb will give you the direction of the torque. Okay, another way, the way that I actually prefer to do it, a second way of doing it, is if you take your fingers and point them in the direction of R, that first vector in your cross product, and then you curl them towards the vector F, then your thumb will still point in the direction of the torque. So R cross F, boom, you get the direction of the torque, or R, put your palm in the direction of F, and the thumb gives you the torque. Those are both ways of doing the right-hand rule, and they both are equally accurate. All right, so let's go back to momentum. So we got torque in 3 dimensions, we got angular momentum, all kinds of fun stuff. So just like with linear momentum, if you have a system, multiple different objects in a system that are free from any outside force, linear momentum is conserved. Well, guess what? Same concept applies to angular momentum. If you have an isolated system, a system now, since we're talking about rotation, a system that is free of any external torques, guess what? Angular momentum is conserved. A very good example of conservation of angular momentum comes from watching figure skating. All right, so if you watch any figure skating, you're probably just seeing, some pretty impressive skills and also thinking some pretty amazing physics is going on. And what you're seeing when they spin is actually the principle of conservation of angular momentum. If you notice, when they enter the spin, they have their arms and legs usually spread out relatively wide. As they pull their arms and legs in, they start spinning faster. Why is that? Well, again, angular momentum is moment of inertia multiplied by angular velocity. When their arms are spread out, they have more mass at a further distance away. They have a larger moment of inertia. As they pull their arms in, their moment of inertia is decreasing. As their moment of inertia decreases, since angular momentum is conserved, their angular velocity must increase in order to keep the same amount of momentum. So if you decrease your angular momentum, or excuse me, if you decrease your moment of inertia, you must increase your angular velocity in order to maintain a constant angular momentum. So again, ice skating is a perfect example of conservation of angular momentum. So let's do an example problem with this. Who better to have as our example than Sir Albert Einstein himself? So here we have Albert Einstein, and he's going to demonstrate conservation of angular momentum for us. So he's standing on this rotational table that you can see down here. The reason that I put him on this turntable is so that he's in an isolated system. If he's just standing on the ground, this wouldn't work very well, right? Even ice with these shoes probably wouldn't work super well. But with ice skates, ice is a isolated system, okay? But his turntable here is also an isolated system. That sounded like a laugh track, but my wife actually thought my joke was funny. Bonus. Anyway, so what we got here is he's on a turntable, and he's going to hold two 5-kilogram dumbbells out horizontally away from him. So he's a pretty tough guy, you know, holding these dumbbells out here. And he's going to get himself rotating. Since it's Einstein, he can get himself rotating exactly at pi radians per second. So 3.14 radians per second will be his initial angular velocity. And he's going to then, after he gets spinning, he's going to pull his arms in with those dumbbells, decreasing his moment of inertia and increasing his angular velocity. So to figure this one out, I'm asking you to tell me how fast he's spinning afterwards. But to figure this out, you need to know a couple things. One, you need to know the moment of inertia of his body. So his body with the arms out, it's 3 kilograms times meter squared. His body with the arms in is 2.2 kilograms times meter squared. So not a big difference there, but the real difference is going to come from those dumbbells. So when his arms are out, assume that the dumbbells are approximately 1 meter away from his rotational axis, the center of his body. And when they're in, assume that they're about 0.2 meters away from that central axis. With that information, tell me how fast he's moving at the end. So hopefully you pause the video to figure this one out. I'm going to go ahead and walk you through it. So again, we already said we have an isolated system, so we're going to use conservation of angular momentum. That means that the initial angular momentum equals the final angular momentum, and angular momentum is I times omega, right? So I initial omega initial equals I final omega final. Now we want to figure out the final angular velocity, omega final. We know omega initial, it's given to us 3.14 radians per second, but what is I initial and what is I final? A lot of people just want to plug in 3 and 2.2 and call it good. No, that's not good enough because you ignored the dumbbells, right? I initial is really I of his body with his arms stretched out, plus the dumbbells when they're out there. And then I final is I with the hands in, plus the dumbbells in that inner position. So to figure out the overall I value, you need to take the moment of inertia of his body and add the two dumbbells. We're going to treat the dumbbells as point masses. And so for a point mass, it's just moment of inertia is mr squared, right? So you have m, 5 kilograms, times r, 1 meter, quantity squared, and there's two dumbbells, so I multiply it by 2. So 2 times 5 times 1 squared is 10, plus the 3 for his body gives us an initial moment of inertia of 13 kilograms times meter squared. Now in the final situation, similar process, we use the body, 2.2 kilograms times meter squared, plus 2 times the mass of the dumbbell, since there's two dumbbells, at 5 kilograms each, and then multiplied by their distance squared, which in this case is 0.2 meters squared. Doing the math, we get 2.6 kilograms times meters squared. So notice, with just his body, it's a relatively small change in the moment of inertia, but when you add those dumbbells, you get a much larger change. So now we can go ahead and solve for omega final by taking our initial angular momentum and dividing it by the final moment of inertia, plugging in your values. You should find that it's equal to 15.7 radians per second, which I believe is about 5 pi. So boom, box worthy. Einstein's really spinning quite rapidly. So the last thing I just want to kind of talk to you guys about. It's just a cool application of conservation of angular momentum. It's something known as precession. All right. So if you think of a top or even the globe, they're rotating bodies, right? They're spinning. So therefore, guess what? They have moment of inertia. They have rotational velocity. They have angular momentum. And if they're free of any outside forces, like the Earth as it's rotating in space is free of any outside torques causing it to change, so it has a conservation of angular momentum. And its angular momentum keeps it spinning and spinning, and as a result of that angular momentum, it actually wobbles very similar to how a top wobbles. If you ever spin a top, it's spinning very fast on its axis, right? But then it's also kind of wobbling as its axis changes the direction it's pointing all the time. That's as a result of gravity causing its direction of its angular momentum to constantly change, okay? You get the same thing with the Earth. The Earth's axis is actually changing the direction that it points all the time. So right now, our axis points approximately to what we call the North Star, Polaris. If you waited around for about 15,000 years, if Christ has not returned by then, the North Star will no longer be the North Star, or at least Polaris will no longer be the North Star, because our axis will have changed where it's pointing to the furthest opposite in the direction that it's pointing, and it'll be pointing approximately to the star Vega, and it will become the new North Star. Pretty cool application of angular momentum. There's a lot of other fun ones as well with bike tires and so on. But that really wraps up the new information from chapter 11. I'll have a few more example problems for you guys coming in future videos, but have yourselves a box-worthy day.